What if I told you that your head is aging faster than your feet? That time travelers already walk among us, astronauts returning from space, microseconds younger than they should be? That the universe might not have a past or future at all, just an eternal now? And that the now you're experiencing right now might not even exist for someone moving fast enough? Here's another mind bender. Every time you climb a flight of stairs, you're actually traveling through time differently than someone who stayed on the ground floor. The GPS in your pocket only works because engineers accounted for Einstein's bizarre predictions about time warping near Earth, and that feeling when time seems to fly during fun moments, but crawls during boring ones. That's not just in your head. It's a genuine psychological phenomenon with measurable effects on your brain. Welcome to the Veda Cozy Scientist, where we're about to unravel the most mysterious force in existence, time itself. It governs every second of your life, yet slips through your fingers like water. It's the one thing you can never buy more of, yet sometimes it feels like you have too much of it. Ancient philosophers argued about its nature. Modern physicists still can't agree on whether it's even real. And you're experiencing it right now, second by second, even as you wonder what it actually is. Tonight, we're diving into the cosmic rabbit hole of time. We'll explore why waiting rooms feel eternal, while vacations vanish in a blink. We'll discover how ancient Egyptians invented the first alarm clocks for praying monks. We'll ride alongside Einstein as he turns Newton's clockwork universe upside down. We'll peer into quantum realms where time gets fuzzy and possibly disappears altogether. We'll meet the tiny cluster of cells in your brain that acts as your personal timekeeper. And yes, we'll tackle the big question, could you actually travel back in time to meet your grandparents? And what happens if you accidentally prevent your own birth? Before we begin this mind-bending journey, tell me, where in the world are you and what time is it right now? Fitting, isn't it? Here we are, scattered across time zones, each arriving at this very moment in our own unique slice of the clock. Someone watching this is experiencing their morning, someone else their midnight, yet we're all here together in this strange, shared now. If you find this voyage intriguing, hit that like button and subscribe. It helps this cosmic curiosity reach others who might need a moment of wonder. Now, settle in, slow your thoughts, and let's explore the fabric of reality itself. Because somewhere between seconds and centuries, between heartbeats and cosmic epochs, lies one of the universe's deepest mysteries. And tonight, we're going to try to understand it. Time has a funny way of stretching and shrinking, doesn't it? 10 minutes stuck in traffic can feel like an eternity. You watch the clock, check your phone, drum your fingers on the steering wheel, and somehow only 3 minutes have passed. Yet 10 minutes absorbed in your favorite hobby, gone in what feels like a heartbeat. You look up and suddenly an hour has vanished. The strange thing is, clocks tick forward at the same rate, second after second, minute after minute, with mechanical precision. So what's going on? Why does time feel so elastic? The answer begins with your brain, not with physics. Our perception of time, what psychologists call subjective time, is surprisingly flexible, shaped by complex interactions between attention, emotion, and memory. How you feel about time can be radically different from how time is actually passing. In fact, your brain doesn't have a single time detector like it has sensors for light or sound. Instead, time perception emerges from multiple brain systems working together, which is partly why it's so easily distorted. The agony of waiting, picture this. You're sitting in a doctor's waiting room. The walls are beige. The magazines are from 3 years ago. There's a clock on the wall ticking loudly, like it's competing for the world's most annoying sound award. You've been waiting for what feels like 30 minutes, but when you check your phone, only 5 minutes have passed. Why does waiting feel so excruciating? Your brain is starved for stimulation. when nothing interesting is happening. No conversations, no engaging content, nothing to occupy your attention. Your focus turns inward. You become hyper-aware of each passing second. Your internal attention spotlight, normally directed at external stimuli, starts monitoring time itself. And paradoxically, the more you watch time, the slower it seems to move. It's like the watched pot that never boils, except the pot is your own consciousness. Time has a funny way of stretching and shrinking, doesn't it? 10 minutes stuck in traffic can feel like an eternity. You watch the clock, check your phone, drum your fingers on the steering wheel, and somehow only 3 minutes have passed. Yet 10 minutes absorbed in your favorite hobby, gone in what feels like a heartbeat. You look up and suddenly an hour has vanished. The strange thing is, clocks tick forward at the same rate, second after second, minute after minute, with mechanical precision. So what's going on? Why does time feel so elastic? The answer begins with your brain, not with physics. Our perception of time, what psychologists call subjective time, is surprisingly flexible, shaped by complex interactions between attention, emotion, and memory. How you feel about time can be radically different from how time is actually passing. In fact, your brain doesn't have a single time detector like it has sensors for light or sound. Instead, time perception emerges from multiple brain systems working together, which is partly why it's so easily distorted. The agony of waiting, picture this. You're sitting in a doctor's waiting room. The walls are beige. The magazines are from 3 years ago. There's a clock on the wall ticking loudly, like it's competing for the world's most annoying sound award. You've been waiting for what feels like 30 minutes, but when you check your phone, only 5 minutes have passed. Why does waiting feel so excruciating? Your brain is starved for stimulation. When nothing interesting is happening, no conversations, no engaging content, nothing to occupy your attention, your focus turns inward. You become hyper-aware of each passing second. Your internal attention spotlight, normally directed at external stimuli, starts monitoring time itself. And paradoxically, the more you watch time, the slower it seems to move. It's like the watched pot that never boils, except the pot is your own consciousness. This is also why childhood summers seem to stretch on forever. Think back to being 7 or 8 years old. Summer vacation felt infinite, didn't it? Days were long, each one packed with new experiences, discoveries, adventures. Your brain was constantly encountering novel situations, learning to ride a bike, making new friends, exploring new places, and it logged every bit of it in rich detail. As we get older and routines set in, our brains become more efficient at compressing memories. Fewer highlights, shorter mental reels. We take the same route to work, do the same tasks, see the same people, eat the same meals. Our brains essentially go, oh, this again, and don't bother creating detailed records. The result? Time seems to accelerate. It's not that time is actually moving faster, it's that we're creating fewer memorable moments, fewer mental bookmarks. The years seem to fly by because we're not logging them as carefully as we did in childhood. There's actually a way to counteract this. Deliberately seek out new experiences, travel to new places, try new hobbies, break your routines, learn new skills. When you do this, you're forcing your brain to pay more attention and create richer memories, which can make life feel fuller and longer. Emotion warps time. Emotion is another powerful time-warping force. Studies show that fear and anxiety can dramatically slow our perception of time, while joy and excitement tend to speed it up. But the relationship is complex and sometimes counterintuitive. In dangerous or intensely stressful situations, many people report that time seems to slow down dramatically. There's a theory that in these moments your brain kicks into overdrive, creating denser, more detailed memories, capturing more information per second than it normally would. Later, when you recall the event, All those extra details make it feel like the experience lasted longer than it actually did. This has been tested experimentally. In one famous study, participants were asked to judge the duration of a frightening event, in this case, a backwards free fall from a tall platform. They consistently overestimated how long they'd been falling. It's not that time actually slowed in the moment. Their reaction times weren't any faster than normal. But the memory of the event was so detailed and vivid that it created the illusion of slow motion. People who've been in car accidents often report this phenomenon, the sensation that everything happened in slow motion, that they could see every detail unfold. What's really happening is that their amygdala, the brain's fear center, has triggered an emergency recording mode, capturing far more detail than usual. It's the memory playback that feels slow, not the actual experience. Then there's boredom, which we've touched on but deserves more attention. You've probably heard the phrase, time flies when you're having fun. The opposite, time crawls when you're bored, is equally true, and perhaps even more torturous. Neuroscientists have discovered that boredom doesn't just make time feel slow, it can actually change how our neural circuits process temporal information. The anterior insular cortex, a brain region involved in time perception, shows increased activity during boring tasks, as if it's working overtime to track every agonizing second. Cultural time. Even culture and language shape how we perceive time, which reveals just how much time perception is a constructed experience rather than a direct objective sensation. In English and many Western languages, we often talk about time as if it's a resource or commodity. We spend time, save time, waste time, or run out of it. This metaphor frames time as something valuable that can be managed, budgeted, and optimized, which creates a certain relationship with time that can increase stress and time pressure. Some languages, like Hopi, though this is debated by linguists, don't treat time as a line you move along, but more like a landscape or a set of conditions. This fundamentally shapes how speakers think about past, present, and future. In some cultures, people point behind them to indicate the future because it's unknown and unseen, and in front of them to show the past because it's already visible and known. Quite the opposite of how we usually picture things in Western cultures, where we point forward to the future and backward to the past. The Aymara people of the Andes also have this reversed spatial temporal metaphor. For them, the past is ahead, Naira, and the future is behind, Shipa. This makes sense from one perspective. You can see the past because it has happened, while the future is behind you, unseen and unknown. These aren't just linguistic curiosities. Research suggests these metaphors actually influence cognition and behavior. Studies show that speakers of languages with different time metaphors perform differently on tasks involving temporal reasoning and planning. Our inner clocks, but surely, underneath all these psychological distortions, there must be some kind of biological mechanism ticking away, giving us at least a rough idea of time's passage. There is, sort of. Humans have something called circadian rhythms, roughly 2 4-hour cycles that help regulate sleep, body temperature, and hormone levels. But those are more like daily timers than stopwatches. They tell us when to sleep and wake, but they're not much help for estimating whether you've been waiting for 2 minutes or 10. For shorter periods, seconds, minutes, scientists believe we use a kind of mental timekeeper, often compared to an internal stopwatch. This system involves a network of brain regions, including the basal ganglia, the cerebellum, and parts of the prefrontal cortex. It seems to rely on a steady stream of neural pulses. When we estimate how long something takes, we're subconsciously counting those pulses. But here's the problem. We're not always good at it. Our time estimations can be wildly off, especially when we're multitasking, distracted, or emotionally charged. Our internal stopwatch is more like a sundial in cloudy weather, sometimes accurate, often not. There's even a psychological phenomenon called the return trip effect. Have you noticed that the journey back from somewhere often feels shorter than the trip there, even if it takes exactly the same amount of time? On the way to a new destination, your brain is actively processing new information, new roads, new landmarks, new scenery. It's paying close attention and creating detailed memories. On the way back, it already knows the route, so the experience feels faster. The brain is on autopilot, and fewer detailed memories are being formed. And let's not forget the most universal distortion of time known to humankind, the snooze button. Somehow, those 9 minutes between alarms feel shorter than any other 9 minutes in the universe. While there's no hard science behind that specific feeling yet, it's probably another case of disrupted sleep, incomplete consciousness, and our fuzzy internal stopwatch just throwing up its hands and giving up. The bottom line. So, what is time? At least as we experience it. It's not just a number on a clock or the shadow of a sundial. It's a feeling, a perception, a complex construction built from memory, attention, emotion, and expectation. It changes with our mood, our age, the language we speak, and what we're paying attention to. It speeds up when we're in love, slows down when we're scared, and sometimes seems to vanish altogether when we're fully immersed in the present moment. And while physics may eventually explain what time is on the grandest cosmic scales, our personal sense of time will always be something deeply human, wobbly, wonderful, subjective, and at times delightfully unreliable. Understanding this doesn't make time any less mysterious, but it does help us appreciate why two people can experience the same hour so differently, why childhood felt so long and adulthood so short, and why that last minute before the weekend can feel like an eternity. A measuring the unmeasurable from sundials to atomic precision. Ancient timekeepers. If time is mysterious, then our efforts to measure it are a testament to both human ingenuity and impatience. From ancient sundials to atomic clocks, we've spent millennia trying to wrangle this invisible force into something we can see, count, and ideally schedule around. Because while time may wait for no one, humans are very fond of asking it to hold on just a minute. Let's start in the deep past, when the first timekeepers weren't clocks or calendars, but the sky itself. Our ancestors were expert observers of the heavens, the rising and setting of the sun, the phases of the moon, the seasons shifting like slow tides. These were nature's earliest calendars. No batteries required, no daylight saving time confusion. The ancient Egyptians were among the first to formalize timekeeping. Around 1500 BCE, they built towering obelisks that acted as giant sundials. By tracking the shadow's movement across the ground, they could divide daylight into segments or hours. There was just one problem. The lengths of these segments changed with the seasons. An hour in summer, when days were long, was quite a bit longer than one in winter. It wasn't exact, but it was good enough for organizing society, planning harvests, timing prayers, and keeping track of when the pharaoh wanted his lunch, which even then was probably running late. Water clocks, or clepsydra, came next. These ingenious devices were used by Egyptians and later by the Greeks and Chinese. They measured time by the steady flow of water from one vessel to another. The beauty of water clocks was their consistency. Unlike sundials, they could work at night and on cloudy days. Some were surprisingly elaborate, featuring gears, figures that chimed the hours, or even mechanical birds that sang. You could say they were the original smart devices, just considerably wetter. Meanwhile, halfway across the world in Mesoamerica, the Maya were developing intricate calendar systems that tracked lunar and solar cycles with astonishing accuracy. Their famous long count calendar could measure spans of time covering thousands of years, and their astronomical observations were so precise that they could predict eclipses. For a civilization that didn't have metal tools or beasts of burden, their grasp of celestial mechanics and time was nothing short of cosmic. Medieval mechanisms back in Europe, it wasn't until the Middle Ages that mechanical clocks began ticking their way into history. At first, these were large, unwieldy contraptions installed in church towers and monasteries. They didn't have faces or hands that we'd recognize today. Instead, they just rang bells at regular intervals to mark the passing hours, mostly to remind monks when to pray, eat, and sleep. You might say monks were the world's first alarm clock users, albeit far more serene about 6 a.m. wake-up calls than most of us. One of the first major leaps forward came in the 14th century with the invention of the verge escapement. This was a clever bit of engineering that allowed for a more controlled and regular release of energy in a clock's mechanism. Think of it as the first reliable tick-tock rhythm. This innovation made it possible to build smaller, more reliable mechanical clocks. Eventually, clockmakers added dials and hands so people could actually see what time it was, not just hear it toll across town. From there, the pace of innovation began to tick faster, pun intended. Clockmakers became artisans, crafting increasingly sophisticated timepieces. Clocks moved from church towers into wealthy homes. Portable clocks appeared, though calling them portable is generous. They were more like small furniture pieces you could technically move if you had enough servants. The pendulum revolution. By the 17th century, a major revolution arrived: the pendulum clock. We have the brilliant Dutch scientist Christian Huygens to thank for this. In 1656, Huygens realized that a pendulum swings at a remarkably consistent rate, determined by its length and the force of gravity. He built the first pendulum clock, and suddenly timekeeping accuracy improved dramatically, from being off by several hours a day to being accurate within a minute a day. That's a staggering improvement. If time was a wild horse, the pendulum was the saddle that finally let us ride it with confidence. Pendulum clocks became the gold standard for precision timekeeping and remained so for nearly 300 years. They were installed in observatories, government buildings, and railroad stations. They brought standardization to a world that desperately needed it. Maritime chronometers. The need for even more precise timekeeping became absolutely critical during the age of exploration. Sailors could easily determine their latitude by observing the sun or stars, but longitude, their east-west position, was a much harder problem. Calculating longitude required knowing the exact time at a fixed reference point, like Greenwich, England, and comparing it to local time at sea. The problem was so severe that ships would get lost, run aground, crash into rocks, or sail aimlessly for weeks, wasting supplies and lives. In 1714, the British government offered a huge prize, the Longitude Prize, for anyone who could solve this problem. Enter John Harrison, an English carpenter and self-taught clockmaker with an obsessive attention to detail. Harrison spent decades of his life inventing marine chronometers, ultra-precise clocks that could maintain accuracy despite the rocking and rolling of a ship at sea, temperature changes, humidity, and salt air. His fourth model, known as H4, it looked like a large pocket watch and was accurate to within a few seconds over a transatlantic voyage. Harrison's chronometer changed navigation forever and probably saved countless lives. It earned him recognition, though getting the full longitude prize required years of persistence and political wrangling. He finally received it when he was 80 years old, along with a well-deserved place in history and possibly a few eye rolls from old-school navigators who'd been using stars and gut instinct until then. The quartz era fast-forward to the 20th century, and we entered the age of quartz. In the 1920s, scientists discovered that quartz crystal oscillators could revolutionize timekeeping. When subjected to an electric current, quartz vibrates at an incredibly stable and predictable frequency. Exactly 32,768 times per second for the standard tuning, fork-shaped crystals used in watches. These vibrations could be used to keep time with far greater precision than anything mechanical. Suddenly, clocks and watches could be cheap, mass-produced, portable, and accurate enough to keep trains running on time, or at least give us no excuse when they didn't. Quartz watches became ubiquitous, affordable, and reliable. Today, that $20 watch on your wrist is more accurate than the finest mechanical chronometers of Harrison's era. Atomic perfection, but even quartz has its limits. If you want to know the most accurate time on Earth, time so precise that it's almost philosophically absurd, you'll have to go atomic. Atomic clocks, first developed in the 1950s, measure time using the natural oscillations of atoms, usually cesium 133 or rubidium. These atoms, when hit with microwave radiation at just the right frequency, transition between two energy states in an incredibly consistent way. A cesium atom, for instance, oscillates exactly 9,192,631,770 times per second. That number isn't just impressive trivia. It's the official definition of a second according to the International System of Units, SI. Think about that for a moment. The second, one of our most fundamental units of time, is now defined by the behavior of atoms. It's no longer based on Earth's rotation or the length of a day, which actually varies slightly. It's based on quantum physics. These atomic clocks are so precise that if you ran one for 100 million years, it would be off by less than a second. That's great news, assuming you have 100 million years to wait around checking it, though you might want to bring snacks. Today, atomic clocks are used to synchronize everything our modern world depends on. GPS satellites, which need nanosecond precision, internet servers, telecommunications networks, financial trading systems, and scientific experiments. Without atomic clocks, your phone's map wouldn't work, your bank transactions would descend into chaos, and half the world would miss their Zoom calls, which, depending on the meeting, might not be entirely unwelcome. The paradox? And yet, despite all this precision, despite our ability to measure time down to billionths of a second, time still feels strangely personal and slippery. We can divide it into hours, minutes, seconds, milliseconds, nanoseconds. We can watch it scroll by on digital screens. We can synchronize clocks around the world to atomic perfection. But no matter how finely we slice it, we each live it differently. So why did we begin measuring time in the first place? Some historians say it was to regulate prayer in monasteries, others to organize agriculture and harvest timing, mark the seasons, or schedule trade caravans. But maybe, just maybe, it's because humans, for all our love of stories, art, and stars, are deeply comforted by rhythm. The steady beat of time, no matter how elusive or relative it truly is, gives shape to our days. It offers order in chaos, predictability in an unpredictable world. A tick, a tock, a tiny whisper from the universe saying, "You're here now, this moment exists." And that, after all, is what time has always been for us. Not just a measurement, but a companion on the journey. Newton's clockwork universe absolute time. The grand stage for most of history, time was local. It rose with the sun and ended with stars. Then came Isaac Newton, who wanted to pin down the universe itself. Newton gave us a model dominating science for over 2 centuries. In his view, space and time were like a grand invisible stage where the universe's drama unfolded. Actors, planets, apples, cannonballs moved about, but the stage never changed. Time was absolute, ticking at a constant rate everywhere for everyone. Newton wrote, "Absolute, true, and mathematical time, of itself and from its own nature, flows equably without regard to anything external." Time was like a river flowing steadily, regardless of whether anyone watched. Drop an object today or tomorrow, here or another city, and Newton's equations told you exactly where it would be. The power of absolute time. Newton's absolute time gave scientists a powerful tool for describing motion precisely, synchronizing events, creating predictions. Want to calculate planetary orbits, pendulum swings, or cannonball trajectories? Plug it into Newton's framework. Time was universal, the same everywhere, ticking in perfect harmony. Dissenting voices, not everyone agreed. Philosopher Gottfried Wilhelm Leibniz, Newton's rival, argued time wasn't some universal backdrop but a measure of change, a way of describing event order. Without events, no time. It's not a thing itself but a relationship between things. Imagine a clock in a completely empty universe, ticking in darkness. For Newton, it's measuring time. For Leibniz, it's a fancy paperweight with no one to notice. Time only has meaning when things happen. Classical success Newton's ideas became the foundation of classical mechanics, working beautifully for centuries. It described falling objects, swinging pendulums, planetary motion, everything. Clocks became more precise, navigation improved, engineering leapt forward, but cracks eventually appeared. In the 19th century, scientists studying light and electromagnetism noticed something strange. Light's speed was always the same, no matter how fast you moved. That didn't make sense in Newton's universe. If a car speeds up, shouldn't it catch light a little faster? But it didn't. Light always sped away at the same pace. This problem simmered until a young patent clerk named Albert Einstein would take Newton's absolute time, give it a polite nod, and turn it completely upside down. Einstein's revulsion, relativity and warped time. Time gets weird if Newton imagined time as a steady river. Einstein said, actually, it's more like a wibbly-wobbly trampoline. In the early 20th century, Einstein upended our understanding with relativity, special relativity, and general relativity. Special relativity, moving through time, published in 1905 when Einstein was just 26. Special relativity revealed that physics laws, including light's speed, are the same for all observers regardless of motion. This caused a problem for Newton's absolute time. In Newton's world, people moving at different speeds still agree on when things happen. In Einstein's world, not necessarily. This leads to time dilation. The faster you move, the slower time passes for you relative to someone standing still. Board a spaceship zooming at near light speed, and your clock ticks slower than Earth's. You age more slowly. You'd miss entire TV seasons. This isn't science fiction. It's been observed. Atomic clocks flown on airplanes tick slightly slower than identical ground clocks, proving time really does slow with speed. The twin paradox. The famous twin paradox. Imagine twins. One boards a spaceship flying around the galaxy at high speed. The other stays home. When the traveler returns, they're younger than their sibling, not from great skincare, but because their time passed more slowly. It's not a contradiction, it's relativity. General relativity. Gravity warps time in 1915. Einstein expanded his theory. General relativity deals with gravity, revealing that gravity warps time too. It describes gravity not as a force, but as space-time curvature caused by mass. The more massive an object, the more it bends space-time, like a bowling ball on a mattress. Time runs more slowly in stronger gravitational fields. Stand next to something massive like a black hole, and time ticks slower for you than someone farther away. This has been measured on Earth. Atomic clocks at different altitudes show measurable differences. The lower clock ticks slower. Technically, your head ages faster than your feet. GPS and time, this phenomenon, gravitational time dilation, has real consequences. GPS satellites experience both time effects. Moving fast slows their time, but being farther from Earth's gravity speeds it up. Their clocks are constantly adjusted for these distortions. Without corrections, your location would be off by kilometers within minutes. Technology must wobble with time. The fabric of reality Einstein showed time isn't an absolute universal river. It's stretchy fabric woven with space itself. It expands, contracts, bends, and twists depending on speed and gravity. Your time, the pace you experience the universe, depends on where you are and how you move. Time is no longer the same for everyone everywhere. It's personal, relational. Einstein's work didn't just rewrite textbooks, it changed how we see reality. Time isn't a fixed background, it's part of the dance, shifting with matter and motion. Every second we live is shaped by these subtle distortions. The arrow of time. Why time only moves forward the backwards world? Let's imagine just for a moment that you wake up one morning and find everything running backwards. Toast leaps out of your mouth and lands perfectly buttered on a plate. Your tea grows hotter as you drink it. Raindrops fly upward into the sky, reassembling into clouds. The sun sets in the east and rises in the west. Strange, certainly. Impossible? Well, according to the fundamental laws of physics, not exactly. And that's what makes this so mind-bending. This odd little thought experiment leads us to one of the most intriguing questions in all of science. Why does time seem to have a direction? Why does it only flow one way? The physics puzzle. Here's what makes this question so fascinating. In most of the fundamental laws of physics, from Newton's laws of motion to Maxwell's equations of electromagnetism to the quantum mechanics equations, time doesn't really have a preferred direction. They're what physicists call time symmetric. They work just as well backwards as they do forwards. If you filmed two particles colliding and played it in reverse, the physics would still check out perfectly. No alarms would go off in the equations. No physical laws would be violated. A ball thrown into the air follows the same parabolic path whether you watch the video forwards or backwards. Both directions are equally valid according to Newton's laws. And yet, in everyday life, time feels emphatically like a one-way street. Eggs break but don't spontaneously unbreak. Paper burns but ashes don't reassemble into books. Ice melts in warm rooms but doesn't spontaneously freeze in cold ones. We remember the past but not the future. Cause always precedes effect. We age, we never unage. So why this profound disconnect between the time-symmetric laws of physics and the very obviously one-directional time we experience? Enter entropy. The answer lies in what's called the arrow of time, a metaphor used to describe the one-way direction in which time appears to flow from the past toward the future. And the key to understanding this arrow is one of the most important and occasionally untidy laws in all of physics, the second law of thermodynamics. This law tells us that in a closed system, like say the entire universe, entropy always increases over time. But what exactly is entropy? It's often described as disorder or randomness, though that's a slight oversimplification. More precisely, entropy is a measure of the number of possible microscopic arrangements of a system that look the same, macroscopically. Here's a simpler way to think about it. Entropy measures how many ways the components of a system can be arranged without changing what the system looks like from the outside. A messy desk has high entropy because there are lots of different ways papers and pens could be scattered that would all look equally messy. A perfectly organized desk has low entropy because there are very few arrangements that maintain that organization. The second law says that systems naturally evolve towards states with higher entropy, towards states that are more probable because there are more ways to arrange them. You can scramble an egg, but you can't unscramble it. Why? Because there are vastly more ways for egg proteins to be scrambled than unscrambled. Your desk will naturally become cluttered unless you actively organize it, because there are many more messy arrangements than tidy ones. Socks will always disappear mysteriously in the laundry, but they'll never spontaneously reappear in matched pairs. High entropy triumphs. This tendency toward increasing entropy gives time its arrow. It's why we experience events in a particular sequence. The low entropy past becomes the high entropy future. And once entropy increases, there's no reversing the flow without expending enormous amounts of energy. The arrow of time points in the direction of increasing entropy. The shattering glass. Think of it this way. Imagine a wine glass sitting on the edge of a table. Someone bumps the table, and the glass falls, shattering on the floor into hundreds of pieces. That's a transition from low entropy, intact, organized glass, to high entropy, scattered shards, dissipated energy. It's a very natural, very probable process. Now imagine filming this event and playing it backwards. You'd see hundreds of glass shards spontaneously leap off the ground, perfectly reassembling into an intact wine glass that then jumps back up onto the table. Does this violate any fundamental laws of physics? Technically, no. Every collision, every energy transfer could theoretically happen in reverse. But would it actually happen? Absolutely not. Why? Because it's extraordinarily, fantastically, mind-bogglingly improbable. The number of specific ways those shards would need to collide, with exactly the right energies and angles, at exactly the right microsecond, to reassemble perfectly is so astronomically small that you could wait longer than the current age of the universe and never see it happen. Not impossible by the laws of physics, just impossible by the laws of probability. And that's the key insight. The laws of physics allow for time reversal in theory, but probability stands firmly in the way in practice. The arrow of time emerges not from physics forbidding reverse processes, but from probability making them vanishingly unlikely. The cosmic mystery. This leads to one of the most profound and slightly unsettling questions in cosmology. Why was the universe in such a low entropy state to begin with? Think about it. If entropy must increase, if the universe is constantly moving toward more disorder, there had to be a starting point. Some moment when entropy was incredibly low. Some cosmic equivalent of a perfectly organized desk from which all this disorder could unfold. But why? What set up that initial condition? The leading theory is that the early universe, just after the Big Bang roughly 13.8 billion years ago, was in an incredibly uniform, smooth, ordered state, extraordinarily low entropy. Matter and energy were spread out almost perfectly evenly. There weren't galaxies yet, or stars, or planets, or people losing their socks. Just a smooth, hot, dense soup of particles in a remarkably simple, low-entropy configuration. Over billions of years, gravity and the expansion of space did their thing. Tiny quantum fluctuations grew. The universe got clumpier. Clouds of gas collapsed into stars. Stars formed galaxies. Matter organized into increasingly complex structures. And paradoxically, this apparent increase in organization locally, stars, galaxies, planets, life, is actually an increase in entropy globally. Why? Because gravitating systems are weird. When they clump together, they release energy into the environment, increasing overall disorder. But this just pushes the mystery back a step. Why did the universe start in that particular low entropy state? Why wasn't it already maximally disorderly at the beginning? This is one of physics's biggest open questions, and answering it might require understanding the deep relationship between entropy, time, quantum mechanics, and the geometry of space itself. Some scientists suspect the answer lies in the conditions during cosmic inflation, a period of exponential expansion in the first tiny fraction of a second after the Big Bang. Others wonder if the question is even meaningful from our current vantage point, like a goldfish asking why the water flows through its bowl. Still others propose that our universe might be one of many, and we naturally find ourselves in one with low initial entropy, because only such universes can support complex structures, like us. To ask the question, multiple arrows. There are several arrows, and they all seem to point in the same direction, which is both comforting and curious. The thermodynamic arrow. This is the entropy arrow we've been discussing. Hot things cool down, never the reverse. Mixed things stay mixed. Disorder increases. The psychological arrow. We remember the past, not the future. Why? Because memories are physical traces left in our brains, arrangements of neurons and synapses. Creating these traces is a process that increases entropy. You can't remember the future because it hasn't happened yet, and so no physical traces have been laid down. Memory itself points in the direction of increasing entropy. The causal arrow causes precede effects, never the reverse. You flip a switch, then the light comes on. You don't turn on a light and then decide to flip the switch. This follows from entropy too. The act of flipping the switch adds energy to the system. Light spreads out into the room, photons scatter, and the universe becomes a slightly messier place. Causation flows in the direction of entropy increase. The cosmological arrow, the expansion of the universe itself, gives a sense of direction to the cosmos. Galaxies are moving away from each other. Space is stretching. The universe is cooling down over time as it expands. This expansion provides another arrow. Interestingly, some physicists have wondered, if the universe were contracting instead of expanding, would time feel like it were running backward? That's still a theoretical playground scientists enjoy exploring. An emergent phenomenon? It's worth noting that these arrows, entropy, memory, causality, cosmic expansion, all line up. They all point in the same direction. That's not a coincidence. They're all connected to the same underlying reality. The universe is evolving from a low entropy past toward a high entropy future. But not everyone is convinced that time as we experience it is fundamental. Some physicists argue that the arrow of time is an emergent phenomenon, something that arises only when complex systems like us observe simpler ones like tea cooling or egg scrambling. In some interpretations of quantum mechanics and certain approaches to quantum gravity, time is just another parameter in the equations, not a force, not a flow, just a mathematical label for different states. In this view, the universe doesn't feel time passing. It doesn't experience a flow. Those are features of consciousness, of memory-forming systems embedded within the universe. We feel time because we're complex patterns of matter, with brains that record the past, anticipate the future, and experience the present. The universe itself might just be, all moments existing equally, with no inherent flow, no preferred direction, until you zoom in on subsystems like us, and then the arrow emerges. The beautiful mystery, and that's the curious thing about the arrow of time. No matter how deeply we dig into entropy, probability, thermodynamics, or equations, time continues to be both incredibly real and maddeningly elusive. It's something we ride like a current in a river, but we can never quite step outside of it to see what it really is. We don't know what's ahead. We can't go back. And yet, we live our lives by its rhythm, finding meaning in the sequence of moments, comforted by the fact that the future, however uncertain, is always on its way. So the next time you feel like time is slipping away, remember, it's not lost. It's not stolen. It's just following the one rule it's really, really good at following, moving forward, increasing entropy, and leaving a trail of broken wine glasses, mismatched socks, and empty teacups behind. The arrow of time flies in only one direction, but that one direction is what makes change possible, growth possible, life possible, and stories worth telling. Quantum time, where clocks get fuzzy jazz improvisation physics. If classical physics treats time as a dependable train schedule, quantum mechanics treats it like jazz improvisation. Flexible, mysterious, sometimes dissonant. Welcome to the quantum world, where reality gets fuzzy and time becomes more suggestion than rule. Probability clouds. In the classical universe, you can point to an object and say, it's right there. But in quantum realms, particles don't have neat positions or momentum. They exist as probability waves, mathematical clouds of where they might be. Where does time fit? Surprisingly, time doesn't star in quantum mechanics like it does in classical physics or relativity. It mostly shows up as a background parameter, something we plug into equations to keep things moving. The Schrödinger equation. The Schrödinger equation, foundation of quantum mechanics, describes how a system's wave function, that weird probability cloud, but unlike relativity, time in this equation doesn't bend or stretch. It's just there, a silent spectator, an external stopwatch never changing. This creates a curious split. Quantum mechanics describes state evolution over time, but doesn't explain what time is. It treats time as fixed, absolute, like Newton, while space and matter jiggle unpredictably. The problem of time things get stranger introducing quantum gravity, attempting to merge quantum mechanics with general relativity. These two titans of modern physics don't get along. In general relativity, space-time is dynamic, stretching and curving. Time isn't absolute. It's part of the fabric. But in quantum mechanics, time is fixed, unbending. Trying to unify these views is like choreographing ballet using heavy metal instructions. This leads to the problem of time in quantum gravity. When describing the whole universe quantum mechanically, space, matter, everything, something odd happens. Time disappears. The Wheeler-DeWitt equation, attempting to describe the universe's quantum state, looks like Schrödinger's equation, but without any time variable. It's timeless. No past, no future, just an eternal present, a giant now. Is time emergent? What's going on? Is time real or illusion? Some physicists believe time is emergent, not fundamental, but appearing when you zoom out far enough, like temperature. Individual molecules don't have temperature, but group trillions together, and temperature emerges. Similarly, time might emerge from complex interactions of quantum systems. Others look to entanglement, the bizarre phenomenon where linked particles influence each other instantly across vast distances. Some theories suggest time's arrow, maybe time itself, could arise from quantum entanglement's growth. The more tangled the universe, the more time flows. Many worlds. Then there's the many worlds interpretation. Every quantum event causes the universe to branch into multiple parallel realities. There's no randomness, just infinite timeline splitting. Time isn't a river, it's a vast, ever-branching tree. Every decision creates a new twig. Somewhere, there's a version of you who didn't forget their umbrella this morning. Why time feels solid if time is shaky at the quantum level? Why does it feel so solid? We live in a world where countless quantum interactions average out into smooth, reliable reality. Our brains, made of trillions of particles, are hardwired to perceive cause and effect. We wake, brush teeth, eat breakfast, hopefully in that order. Time for us is a story, a sequence giving meaning to change. Whether or not time is fundamental, we treat it as real. Quantum mechanics reminds us that underneath that comforting narrative lies something far more elusive. Time may not be clock ticking or page turning, but the unfolding of possibilities, evolution of probability, reality's hum tuning itself with every moment. While your watch says it's 10 to midnight, quantum physics whispers, well, yes, from a certain point of view. Your body's ancient clocks, the internal symphony time, isn't just tracked by ticking clocks or orbiting planets. It's humming quietly inside you, in your cells, sleep, appetite, and mood. Whether you're a night owl, early bird, or perpetually groggy pigeon, your body runs on its own internal clock. And it's very old. Circadian rhythms. This internal clock, or network of them, is what scientists call the circadian rhythm, from Latin circa diem, meaning about a day. Circadian rhythms are biological processes following roughly 2-4 hour cycles, regulating when you feel sleepy to how your body processes food. They're found in nearly all living things: humans, plants, animals, fungi, even bacteria. If it's alive and organized, it probably tells time. The master conductor is a tiny brain region called the suprachiasmatic nucleus, SCN, located in the hypothalamus just above where optic nerves cross. This strategic position lets your body clock sync with light. When eyes detect morning sunlight, the SCN gets the memo and adjusts everything from hormones to body temperature. Melatonin in sleep, one of the SCN's most important jobs, is controlling melatonin release, the sleep hormone. Melatonin rises in evening, making you drowsy, and falls in morning to help you wake. It's your body saying, hey, maybe don't watch another episode. Whether you listen is another matter. But circadian rhythms aren't exactly 24 hours. Most humans naturally run about 24.2 hours. Left entirely to our own devices in a cave with no clocks, we'd gradually drift out of sync. Light exposure keeps us anchored. Morning sunlight resets the clock daily, keeping us harmonized with Earth's rotation. Jet lag disrupts this delicate system and things get weird. Enter jet lag, humanity's least favorite travel souvenir. Jet lag happens when your internal clock is out of sync with your external environment, like flying across several time zones. Suddenly, your brain thinks it's midnight when it's lunchtime, and your stomach, liver, and immune system are deeply confused. Different body parts adjust at different speeds. Your brain might reset quickly, but your digestive system still lives in last week's time zone. Artificial light. Another modern culprit is artificial light. Before electric lighting, humans were guided by natural daylight, waking with the sun, getting sleepy when it set. Today, we're surrounded by screens and bulbs emitting blue light, tricking brains into thinking it's daytime. This suppresses melatonin and shifts rhythms later, making it harder to fall asleep and wake up. We haven't become night owls. We've invited neon owls into our living rooms and handed them remotes. Chronotypes, not everyone's circadian rhythm is identical. Some are morning types, larks, who spring out of bed energetically. Others are evening types, owls, hitting creative strides as everyone else brushes teeth. These chronotypes are partly genetic. If you're not a morning person, it's not laziness. Your brain genuinely doesn't believe it should be awake yet. Temperature and performance circadian rhythms also influence body temperature, which drops in early morning and rises throughout the day, peaking late afternoon. That's why athletes and performers often do better later. Bodies are warmer, more alert, running at peak efficiency. Conversely, that's why early morning presentations feel like doing calculus half frozen. Beyond sleep, biological time's influence goes beyond sleepiness. It affects metabolism, immune system, mood, and even medication responses. There's a growing field called chronopharmacology, studying how drug effectiveness changes by time of day. Timing matters. The same medicine might work better morning or evening depending on what it targets and your body's readiness. Universal rhythms plants follow circadian rhythms too, opening leaves to sunlight during day and closing at night. They even anticipate dawn, stirring before first rays hit. This isn't passive light response, it's an active internal cycle persisting in constant darkness. Sunflowers don't follow the sun because they see it. They turn because they remember. In animals, from birds to bees to rodents, circadian rhythms regulate migration, foraging, hibernation. Even fungi have internal clocks governing spore release and growth. All this paints life on Earth as deeply intertwined with time, not the abstract kind measured by atomic clocks, but biological time grounded in light and dark, warmth and cold, hunger and rest, a time pulsing through living things like a gentle drumbeat. So next time you feel tired at 3 p.m. or unusually perky at night, it's not random. its rhythm, your body dancing to an ancient, invisible beat, one that kept our ancestors safe and well-rested long before time zones, digital watches, or double-shot espressos.
Time travel, science, fact, or fiction?
The ultimate question. No discussion of time is complete without asking, can we travel through time? Well, maybe, but it's complicated. Time travel, at least theoretically, isn't entirely forbidden by physics. According to Einstein's general relativity, space-time is flexible, capable of stretching, warping, and under incredibly extreme circumstances, even looping back on itself. Future travel? Already happening? Let's start with the easy kind, traveling into the future. This one's not just possible, it's already been done. Remember time dilation from special relativity? If you move very fast, close to light speed, time slows for you relative to someone standing still. Zoom around the galaxy in a spaceship at near light speed and return to Earth. Decades could have passed here while you aged only a few years. Congratulations, you've time traveled into the future. No flux capacitor required. This has been tested. Astronauts on the International Space Station experience tiny time dilation. They age ever so slightly less than Earthbound counterparts. Not enough to notice without atomic clocks, but enough to prove the principle. They return to Earth microseconds in the future. Technically still on time for lunch. Past travel, the real challenge. But what about the real mind bender, traveling into the past? Here things get trickier. General relativity allows certain solutions permitting backward time travel. Phenomena like closed time-like curves, loops in space-time where an object could return to earlier points in its own history. Like walking a lap around the universe and ending up at yesterday. Wormholes. One proposal involves wormholes, hypothetical tunnels connecting two distant space-time points. If one wormhole end were accelerated to near light speed, then returned, time at that end would lag behind. Step through the wormhole, and boom, you've arrived in the past. In theory, practical problems with wormholes are monumental. First, we're not sure they exist. Second, if they do, they may collapse instantly. Third, keeping one open would require negative energy, exotic and not available at your average hardware store. Building one might be slightly beyond current engineering abilities. Paradoxes. Even if we could travel back, we'd hit sticky paradoxes. The most famous, the grandfather paradox. Go back in time and accidentally prevent your grandfather from meeting your grandmother, preventing your own birth. But if you were never born, how did you go back? It's a loop logic can't untangle. A cosmic contradiction. Possible solutions. Scientists have tried resolving this. Block universe model. All moments, past, present, future, exist simultaneously like film frames. The timeline is fixed and unchangeable. If you go back, everything you do was always part of the past. You can't change anything. You're playing your role in an already written scene. Many worlds. If you go back and change something, you don't alter your original timeline. You create a new branching universe where events unfold differently. You can stop your grandfather from meeting your grandmother, but it only affects that branch. Your original self remains safely anchored in their own universe. Novikov's self-consistency principle. You can't create a paradox no matter how hard you try. If you go back, the universe somehow prevents you from changing the future. Try to assassinate your grandfather and your gun jams, or you trip, or he unexpectedly joins a monastery. The cosmos has built-in insurance against timeline tampering. Where are the tourists? All this remains theoretical and speculative. No one has built a time machine. No one has documented a time traveler, despite internet claims of suspiciously modern-looking figures in old photographs. Physicists still debate whether the math permits or prohibits time loops. One interesting point, If backward time travel were possible, and someone eventually invents it, where are all the time tourists? Shouldn't we be knee-deep in visitors from year 4000? Some suggest time travel might be limited to its invention point. You can't go back before the first time machine. Others think travelers might be incredibly discreet. Or perhaps more realistically, past time travel is simply impossible despite equation teases. The meaning of one-way time may be that's for the best. As much as we fantasize about revisiting the past, fixing mistakes, reliving moments, buying absurd Bitcoin amounts, perhaps time's one-way nature is part of what makes it meaningful. We can't edit our lives like videos. We move forward moment by moment with all the richness, imperfection, and unpredictability that comes with it. Still, it's fun to dream. And who knows, maybe someone from the future is reading this right now, nodding quietly, thinking, ah yes, the primitive beginnings of temporal theory. Does time exist? The deepest question, the philosopher's dilemma. After traveling through clock physics and minute psychology, after bending time near black holes and wondering about wormholes, we arrive at perhaps the strangest question. Does time actually exist? This might sound like a 2 a.m. dorm room question, but physicists take it seriously. Because when you peel back layers of how we experience time and describe it mathematically, something strange happens. It starts to disappear. Presentism versus eternalism. Let's begin with how we usually think of time. For most, it feels like a river flowing smoothly, carrying us from past to present to future. We're all floating downstream, unable to paddle backwards. This is presentism, the philosophical idea that only the present moment is real. The past is gone, the future doesn't exist yet, and now is all there truly is. But there's another idea Einstein's theories helped make famous: eternalism. In this view, time doesn't flow at all. All moments, past, present, future, already exist. The universe is a four-dimensional block, sometimes called the block universe. Time isn't something we move through. It's a dimension we're part of, just like space. In this view, your childhood, your future retirement, everything in between are laid out like book pages. You don't become older. You already are older on some page, younger on another. You're not surfing time. You're a static thread woven into space-time's fabric. Comforting, maybe a little spooky. Also, yes, relativity and the block universe. This concept arises naturally from relativity. Remember, simultaneity, the idea that two things happen at the same time, depends on your motion. Two observers moving at different speeds can disagree about what now means. That suggests there's no universal present moment, making the whole idea of a moving present wobbly. Quantum gravity's challenge, quantum gravity, adds another twist. When combining quantum physics with general relativity, time often drops out of equations altogether. In the Wheeler-DeWitt equation, there's no time variable. None. The universe, according to this view, is fundamentally timeless. Time as emergence. If time doesn't exist at the deepest level, why does it feel so real? One answer: emergence. Time, like temperature or sound, may not be a fundamental ingredient, but arise from more basic relationships, patterns, changes, interactions. Like clouds forming from molecules or waves appearing in water, time might be something our brains extract from how things change. This is similar to perceiving motion in film. A movie is just still frames sequenced rapidly, but our minds perceive flowing narrative. Some physicists suggest time works the same way. What we perceive as time's passage is really the brain stitching together changes in fundamentally timeless reality. Julian Barbour's vision physicist Julian Barbour goes further. In his view, time doesn't exist at all, not even as a parameter. Instead, the universe is a vast landscape of no's, complete, timeless snapshots. These no's don't change or evolve, they just exist. Our experience of time comes from how these no's are structured and how memories are embedded within them. A cosmic photo album with consciousness flipping through pages. It's radical, but raises interesting possibilities. Maybe time passing sensation is a perception feature, not physics. Humans are narrative creatures. We remember the past, anticipate the future, tell stories. We measure time because it helps organize experiences, plan days, understand change. Time is useful, perhaps essential, for sentient beings navigating a changing world. But that doesn't mean it's real like a rock star or mysteriously disappearing cake slice. The counter argument. Not everyone agrees time is an illusion. Many physicists argue that even if time emerges from more fundamental processes, it still has real effects. Clocks tick, planets orbit, radiation decays. If we build a machine that consistently measures change and it agrees with other machines, doesn't that make time real enough? The best answer? Perhaps that's the best answer. Time is real in the same way stories are real. Not because you can hold it or isolate it in a test tube, but because it structures how things happen. It's the script, allowing events to make sense, even if the script is printed on quantum paper, written in a language we don't fully understand. Does time exist? Perhaps not the way we think. It might not be a flowing thing or ticking clock behind the scenes, but it exists in our experience, biology, culture, and equations. It exists in how we live and remember, in every heartbeat and bedtime story. And maybe that's enough, because whether time is fundamental or emergent, real or imagined, it gives shape to our lives. It reminds us everything changes, moments are precious, and somewhere in the universe's fabric, you are quite timeless here. Dear listener, we've arrived at the end of our voyage, or perhaps just another moment in the vast looping sea of them. We've wandered through ancient sundials and atomic clocks, ridden Einstein's warping space-time waves, puzzled over paradoxes, and stared down whether time exists at all. We've seen that time is not just one thing, but many. A rhythm felt in the body, a trick played by memory, a wrinkle in gravity, a story told by change. Here you are, a little farther along your own timeline than when we began. Was it seconds, minutes, an hour? Or did the flow of words stretch and shrink, like they often do when the mind softens into contemplation? So let me ask once more, where are you right now? And what time is it in your corner of the world? Funny, isn't it? After all this talk about time being relative, flexible, maybe even imaginary, we still anchor ourselves to it. A glowing number on a screen, the hush of evening, the feeling of winding down breath by breath. Time may be slippery, strange, and possibly a complete illusion. But right now, in this moment, it's just you, these words, and the slow rhythm of understanding. Whether time is the universe's heartbeat or merely the story we tell ourselves to make sense of change, one thing remains clear. We live in it, through it, by it. And in exploring time's mysteries, we've touched something profound. The realization that every moment, however measured or misunderstood, is uniquely ours. Time doesn't belong to clocks or equations. It belongs to lived experience, to memories made, to futures imagined, to the present embraced. So wherever and whenever you are, remember, you're not just in time. You are time itself, flowing, changing, experiencing the universe moment by moment. And that, perhaps, is the most beautiful mystery of all.